Okay, so now we're going to start chapter 7, which deals with, as you can see on the screen, with the topic of atomic structure. And let me just say that in this chapter, well, two things. One, in this chapter and the next chapter, we'll be dealing specifically with the structure of the atom, mainly with respect to the electrons. As we know by now, the atom is made up of three different particles: protons, electrons, and neutrons. All right. So we'll be dealing with the electrons, which of course are outside the nucleus, and not the protons and neutrons, which are inside the nucleus. The arrangement and the discussion concerning the nuclear particles will be left for General Chemistry 2, when you'll be studying nuclear chemistry. But in this chapter, chapter 7 and chapter 8, we'll be dealing mainly with how the electrons are arranged in the atom. So that's one thing. The other thing I want to say too about this chapter and the next chapter is that the topics that will be covered will be very abstract, very abstract. I remember when I was a student exposed to this for the first time, it took me some time to actually get some feel for what the topic is all about because of the abstractness of the topics, all right? And there's a reason why that is, because this area is, to be perfectly honest, not fully understood by even persons who are experts in these topics, all right? So if you have some challenges understanding this, I can totally understand. I can totally appreciate this. And I would strongly recommend that you listen carefully to the videos. Now, one thing I will say is that I'll be skipping a lot of details that would probably make things clearer. And that's because of basically the amount of time that would be needed to explain a lot of things, all right? But I would strongly recommend that you take your time. If you need to stop a particular video at a particular point and rewatch it, you probably need to do so. And I would strongly recommend that you contact me if you have any further questions, if you know what you're watching just simply doesn't make sense to you, all right? Okay, so with that out of the way, let's start with a discussion of chapter 7. And the first thing we're going to talk about, and this will be a very brief history of how do we arrive at our current modern version of the atom. So way back when, back in the day, as they say, there was a point of view that small particles like electrons and atoms and so on behave pretty much the same way as regular sized objects like a ball or, you know, a car or whatever. So basically, it was thought that the laws of Newton's or the laws of motions that were put forward by Newton would apply equally to regular sized particles or regular sized objects as they would to small particles like electrons. Well, as a result of experiments with light, it was shown that this was not the case, right? At the very microscopic level, particles behave much differently compared to regular sized atoms. And this brings us to the quantum theory, which we're going to discuss in some detail later on in this chapter. And based on the quantum theory, we now have a more accurate representation or model for how atoms and in particular electrons behave, all right? So that's basically a brief overview of the history of how do we arrive at the modern understanding of the nature of atoms and how the electrons behave in atoms. All right, now, firstly, we're going to deal with the discovery of electrons. And what we're going to talk about is this phenomenon known as cathode rays, right? These rays were discovered by this guy here. I don't know if I'm pronouncing his name correctly, Johann Hittorf in 1869. And he basically came up with this design right here, this setup, which consists of a tube which is evacuated, so it is connected to a vacuum pump, so all the air is sucked out of it. And you have two electrodes here. You have the cathode, which is connected to the negative end of the electricity source, which could be a series of cells, and the anode, which is connected to the positive end of the electricity source, right? And typically in an electric circuit, a part of the circuit would be a switch, which is not shown here. In any case, when the switch is turned on, then the circuit is closed, and what will happen, what is observed, is that a stream of particles will be emitted from the cathode and would travel along straight lines to hit the anode, all right? So these rays were called cathode rays, but it's actually a stream of particles, all right? And these particles were later on discovered to be negatively charged, and they were called electrons, all right? So as always happens in any new scientific discovery, when somebody discovers a particular phenomenon, then all other scientists try to rush to it to find out more about the phenomenon so that they can publish their own findings about it. So that's exactly what happened in this case here. So this is basically a replica of the experiment that was done to discover cathode rays. And some things were discovered initially. It was discovered that these particles, when they hit or impact certain materials like glass and other materials, they fluoresce, which basically means that they light up, all right? Another thing that was discovered about these particles is that they do travel in straight lines, but if you place near it a magnet or some source of electric fields, then that straight line travel would be deflected towards the magnet or according to the direction of the magnetic, or I should say electric field, all right? So those are the first two things that were discovered about the cathode rays very soon after they were discovered. And then later on, a guy by the name of J.J. Thompson, he made some modifications to the original design in order to make some discovery about the nature of these particles. So let me just briefly describe what you have here. So this is the modification of the cathode ray tube that was discovered earlier. Here we have the cathode connected to the electricity source, and one of these two metals here, cylindrical metals, is an anode. This one, in fact, but it is basically a slit is made into it so that when the cathode rays are produced here, they will not only be attracted to the anode, but they'll have enough energy to pass through it. So it passes through this slit, and then there's another cylinder with a slit right here, passes through that slit to form a narrow beam. And then it goes into this region here. Now, let me explain what is happening in this region. In this region, you have two powerful magnets here, and you have two plates here, which are themselves connected to an electricity source. So here we have a cathode and an anode, or actually the negative electrode is the cathode, and this is the anode. And what J.J. Thompson was able to do with this setup was that he was able to adjust the magnitude and direction of both the magnetic and the electric fields. And based on those manipulations, the cathode rays will be deflected, and basically looked at the effect that the electric and magnetic field quantitatively would have on the angle of deflection of the cathode rays. So we have a scale here at the end of this part of the apparatus here, which basically measures the angle of deflection, all right? So that's basically J.J. Thompson's experiment, and I won't go into all the details in terms of the calculations that he performed based on the data collected from this experiment. I'm just going to show you that he determined, based on this setup, the mass to charge ratio of the electron. So if you take the mass and divide it by the charge, then that is what he was able to determine based on this experimental setup. And he found that the mass to charge ratio is equal to minus 5.686 times 10 to the minus 12 kilograms per coulomb, all right? So that's what he was able to find out. And let me just say here, you may not know this, or you may not have met this before, so I'm going to show you now. The unit of charge, the metric unit of charge, is called the coulomb, and it's represented by uppercase C, right? So mass is in kilograms and the charge is in coulomb, and therefore that's why the unit of mass to charge ratio is in kilograms per coulomb. Another thing I want to notice is, I want you to note, is that since the charge is negative for the electron, we have a negative sign here, all right? Okay, so that's basically one important discovery that was made by J.J. Thompson, which was an important step in our understanding of the nature of the electrons. Now, as I said before, what he determined here was the mass to charge ratio. But scientists, of course, are not satisfied with that. They want to know what the mass is and what the charge is, all right? So another guy by the name of Millikan came up with this setup, right? Millikan, I think he was from Holland, if I'm not mistaken. And well, before I say that, it was after that that the term electron was coined by a guy by the name of Stoney. And then Millikan came up with this experiment in order to determine the charge on the electron. So let me try again to briefly describe how the setup of this experiment. This experiment consists of two plates which serve as electrodes. So this is positively charged, this is negatively charged, and they're connected to the electricity source. You have a container here, a little bottle right here, which is fitted with this spray apparatus here, and it contains oil. Now, to be perfectly honest, I don't remember what kind of oil was used here. In fact, you know what? Let me see if I can find out very quickly. Oil used by Millikan. And what type of oil did he use? Okay, they said vacuum pump oil, which sounds to me like some sort of mixture of hydrocarbons, you know, like gasoline or diesel or, you know, the engine oil. Well, not the synthetic one that you'd put in your motor vehicles. So that's what it sounds like to me. Let me just click on this just to get some further information. Okay, so according to this, Millikan tried to use various types of droplets. J.J. Thompson tried to use water droplets. Of course, I'm not surprised. Water is cheaper than pretty much any other liquid. Millikan apparently found, okay, I won't read through all of this, but basically they settled on vacuum pump oil. So apparently vacuum pump oil was the oil that best worked for this experiment. Okay, so going back to this. So basically the oil is sprayed onto the surface here. One thing I should have mentioned is that the positively charged plate, or the cathode, has a very tiny hole which allowed for droplets to fall through. And when the droplets are falling through here, they're exposed to a source of ionizing radiation. So what this radiation does is provide energy to the droplets so that it knocks the oil, or it knocks an electron off the oil droplet. So therefore, we end up now with a charged droplet. So because it's charged, it is possible to suspend using the electric field. You have to vary it. So basically, it will be suspended in between the two plates. And the telescope here is used to view the oil droplet as it is suspended. So basically, based on that, we can determine the charge that is present on the oil drop, because the force that is used to basically hold up the oil drop going upwards will be equal to the same force which is due to the gravitational pull of the Earth, all right? And based on that balance, we can determine the charge on the oil droplet. Now, I won't go into all the calculations for that. I'll leave that for you to read upon. If you are somebody who has to do physics, I'm quite sure that you will meet this experiment as well as the one that was done by J.J. Thompson. And in that case, you'll definitely go into the actual calculations involved, all right? But we won't go into that here in this chemistry course. All right, so as a result of this experiment, Millikan determined that the charge on the electron is equal to minus 1.602 times 10 to the minus 19 coulomb. So now we have two things. We have the mass of the electron, or I should say the mass to charge ratio of the electron, and we have the charge on the electron discovered by Millikan, right? So therefore, if we have, let me write something down here. If we have the mass to charge ratio, write it here. If we have the mass to charge ratio, right, and we multiply that by the charge, then that would give us the mass, right? So we can easily calculate the mass given the mass to charge ratio, which was discovered by J.J. Thompson, and the charge on the electron, which was discovered by Millikan. So based on that calculation, the mass to charge ratio times the charge, Millikan calculated that the mass on the electron will be equal to 9.109 times 10 to the minus 31. In fact, let's confirm that. So from before, we saw that the mass to charge ratio is minus 5.686 times 10 to the minus 12 kilograms per coulomb, and the charge on the electron is minus 1.602 times 10 to the minus 19 coulombs, right? So the coulomb units cancel out. So your final units would be kilograms. And let me do this on my calculator here. So 5.686 times 10 to the minus 12 times 1.602 times 10 to the minus 19. So that is indeed correct. I got here 9.1089 and some other digits times 10 to the minus 31. So that's basically how we now know these three important facts about the electron: the mass to charge ratio, and then the charge on each electron, and then the mass based on those two. So it turns out that the mass of the electron is equal to that. Okay, we're going to stop this video here, and the next topic we're going to cover in the next video is how do we now know how the electrons are arranged in the atom. So we're going to do another bit of historical look at how we arrive at our current understanding of the arrangement of electrons in the atom. All right? Okay, until next time.